This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software.
For Software Engineering Radio, this is Robert Blume. Today I have with me Sean Knapp. Sean is the founder and CEO of Ascend.io. Prior to Ascend, he was a co-founder, CTO, and chief product officer at Uyala, and before that, an engineer at Google. Sean has degrees in computer science from Stanford University. Sean, welcome to Software Engineering Radio.
Thanks for having me, Robert.
We are going to be talking today about data pipeline automation. Let's start out with, what is a data pipeline?
Yeah, I think a data pipeline has morphed over the course of time. Traditionally, people have really thought about data pipelines in the notion of an ETL context, where we're extracting data from one location, moving it around, potentially transforming it, and dropping it into another. That could be pulling data, whether it's from a sensor in an IoT landscape or out of a spreadsheet, or moving a file from one file system to another. And oftentimes, the data pipelines are moving data into a data warehouse or into a BI application. Over the course of the last 5-10 years, data pipelines have become even more important because they've not just been moving records, but they've been moving large volumes of data and information, and they've been doing more complex things to that data. So everything from really advanced analytics to machine learning and tackling far more interesting complex use cases as industries have matured and evolved.
You're talking about large volumes. How big?
It's interesting that we, for example, work with folks who do everything from they're moving around thousands of records per day, or just kilobytes of information, to people who are pushing around billions, and actually the largest is even over 1 trillion records per day, where they're moving around. And so data pipelines are really designed, hopefully, are designed well to cater to pretty much any scale.
If you went into a business, maybe you could give an order of magnitude. How many pipelines does a typical business have?
Yeah, so we see smaller businesses and smaller teams may only have a dozen or a few dozen data pipelines. Oftentimes, it's a data pipeline. It corresponds to how many data sources you have, whether it's entities coming out of your transactional databases, or how you're collecting data from users inside of your applications. And so that's usually one of the things that dictates how many data pipelines you have. The second thing, and this is what usually can create a pretty large explosion of the number of data pipelines, is frankly how many data products, derived data sets you're creating on top of those. And oftentimes that can lead to hundreds of data pipelines.
We're going to be talking about a bit more rigorous way to think about data pipelines, but I'm wondering if this is like another area we've addressed, which is business process automation, where every business has business processes. They just didn't know it, like the famous character in literature who didn't realize he was speaking prose.
Yes, it is true. I'd say on a weekly basis, we talk with a lot of different companies out there, and you'll see oftentimes they're even talking about, oh, well, we don't do data pipelines. We collect all of our data in our data lake and or our data warehouse, and we use ELT, the extract load transform, where you're processing data as you query it out of a data location, like a lake or a warehouse. And as we dive in deeper, they end up actually having huge numbers of very ad hoc, like informal data pipelines that are moving data into that lake or into that warehouse, or taking all of that raw data and compressing it down and refining it and enriching it so that their actual EOT style queries are faster and more efficient. And so as you start to peel back a few layers, they really very quickly realize they have pipelines all over the place, just didn't realize and weren't thinking of them as data pipelines themselves. So yes, totally, wholeheartedly agree.
So what are the typical building blocks in pipelines?
Yeah, so when we think about the building blocks inside of a typical pipeline, there's a couple of ways of thinking about it. One is obviously the raw technologies and capabilities you need. Those usually boil down to somewhere to store the data, which can be a lake, it can be a warehouse. You need tools to process the data. Oftentimes that's Spark or Kafka or the warehouse itself to process the data. And then the third ingredient, building block you usually need is some sort of orchestration tool. The thing that's keeping tabs on what processing should run on what piece of data, when, and why. So those are sort of the three categories of sort of raw components. Then when we think about more logically what we're doing with a data pipeline, it usually conforms to the data lifecycle itself. So first, how do I ingest the data, collect it from a bunch of different locations, get it into at least a standard storage format, oftentimes snappy compressed Parquet files, if it's in your lake. And then once you get your data ingested, you start to go through the stages of cleaning that data, normalizing it, and then you'll start to go through the stages of enriching it, joining different data sets so you can get richer records that then usually roll into and start to fork out from there into advanced analytics, machine learning pipelines. And that's where you really get to start to do a lot of the really interesting work on the data and start to generate these derived insights and derived data products. So those are usually the 3 or 4 stages.
And generating data sets that you are going to use as training data for machine learning models, or if they're already trained, you may be running the models against that data.
Yeah, a little bit of both on the ML side. We spend more time with folks who are generating a lot of these curated high fidelity data sets to train the models on, is usually where, at least at Ascend, most of our customers use us for. And then on the analytics side is, for example, if you're collecting 2 billion data points a day of users who are using your app, right? You can't do ad hoc queries very cost effectively and efficiently against 2 billion data points every single day for your BI report. And so creating these, whether you call them data cubes or just sort of compressed roll-ups of data, so that you can then query them very quickly off of not 2 billion raw records per day, but can be compressed down to a data set that's in the millions or less. That's what we see a lot of people using those downstream data pipelines for.
So are we largely talking about things that are, let me call it isolated pipelines, or data comes in from some original source? Let's say it's price quotes or temperature sensor, goes through some pipeline, reaches the end point where people can do analysis on it? Or are we also talking about data that is already in the enterprise, like you have an OLTP database from your website and now you need to get that data somewhere else so people can do something else with it, and maybe even you start chaining pipelines together?
Totally. That's a really great point, which is pipelines are like these really flexible Lego building blocks where all of them are different sizes and shapes oftentimes, but you compose them together. And what we see is this huge movement right now to not just have a big data pipeline that's like, the beacons from your users that are using your application, but we see a huge amount of interest in, I want to grab all my data out of my OLTP database. I need a CDC pipeline that's getting that into my unified data store so I can actually do aggregate analysis on top of all of the data that my company has.
Okay, so every business then is pulling data out of an OLTP database and putting it in a data warehouse. So whether they call it a pipeline or not, they have a pipeline.
Very true.
Okay,
Yes.
and let's pick that as a canonical example. You just run a big query that selects out of one database and inserts into another, or is there something in between that's doing something to the data?
Yeah, it's a good question. Hopefully, there's something in between that's helping to optimize that a little bit. For example, a really simple approach is if you're trying to replicate the data you have in your OLTP database inside of, let's say, your data warehouse or your data lake, there's usually a couple of different approaches. A CDC pipeline that isn't actually querying the database, but going off of the CDC or the replication logs of the database itself is a really common paradigm because you're not beating up on your core OLTP database. If you don't have that, a lot of other folks usually will then try and directly query that database using things like last modified time to just get the changes in the data, because you're trying to at least, the biggest fear is always running on a big data system. You can very easily crush your OLTP database. And so you're trying to, as efficiently as possible, take the data out of there and get it into a system that is much bigger and much stronger. And what we'll find is oftentimes a good practice is to, at least at the first stage of that pipeline, to not perform any radical transformations on that data. It's safer to actually keep a copy of that data in cheap storage, put it in S3 GCS, Azure Blob Store, something where you're paying a cent or two a gig. And you can keep a copy of that because you can always go back to it if you need to. And then this is what's really cool about data pipelines and ETL is it's never really one transformation. It's not really ETL. It's usually something that's closer to a regular expression of like ETL plus, where you're constantly, ETL, TL, TL, and you're making cascading transforms and dropping off those derived data sets where appropriate.
You dropped the acronym in there, CDC. Would you define that for listeners, please?
Sure. CDC is change data capture. One of the things that is really interesting about sort of a database, which is designed for high levels of mutability and updates to individual records, is trying to capture all of those changes over time and get those into your data lake or your data warehouse is really valuable. So you can just get those deltas and apply them to the other copy of data you have elsewhere.
Are we generally talking about things that live in the batch mode where you're doing a chunk of data runs in a batch window, maybe next day or an hour later you do another chunk, or the streaming world where every little bit or every minute of data is trickling through the pipeline into the endpoint?
Yeah, what we're seeing is a hybridization of batch and streaming. When we look at how a lot of the industries evolved over the course of time, we all started with batch, and it was like a nightly cron. You started at 1 a.m. to make sure all of your log files showed up in your HDFS cluster, and then you started crunching out a ton of data. And the pendulum swung for a while really strongly towards streaming and trying to push everything through streaming very, very quickly. But the reality is you actually want both, and you need a hybridization of those two. Some form of batch processing allows you to do more complex analysis because you can correlate data that would not naturally be within the same time window. And some form of streaming allows you to do really rapid propagation for analysis that needs to happen very quickly. And so this notion of hybridizing batch and streaming has actually started to get rolled up into the concept of data flows, where we, rather than say, I want to run this pipeline every 10 minutes or 10 hours, or pick your interval, and on streaming, which is it's just continuously running, but I have a tight window of data. The notion behind a data flow is not overly new, but it's more of a descriptive model that says, here's the correlation of data, here's how I want to process it, and you try and move data through as quickly and efficiently as you can based on the calculations itself. And so, for example, how we've implemented inside of Ascend is using high frequency microbatch, where we grab small chunks of data and move them through as efficiently as we can based off the availability of the data itself.
Use the word data flow. I have not run across this. Is this well understood or agreed upon abstraction in this field?
Uh, it's, as a generic term, yes, not in the big data notion yet. When we talk about data flows, and the concept's been around for a while, Google, when they actually first created Beam, Apache Beam, had branded it as Dataflow and actually pulled that back and open sourced it as Apache Beam and kept their branded in Google Cloud notion of Dataflow. And the reason being that, well, one, obviously they needed to separate the branding, but as they describe the notion of a data flow, Beam does a better job of hybridizing this notion of batch and streaming and focuses more on the data itself as opposed to the time synchronization you're trying to apply to it.
When I asked you about building blocks, you mentioned the orchestration layer as one of the building blocks. I'm pretty sure that a lot of organizations are not using orchestration layers. And when we have talked to other guests about workflow process automation, that is also the case there, that implementations are, especially if you don't conceive of what you're doing as an instance of a much more general class of problems that has a general solution. If you go into organizations that are not using an orchestration layer, how are these pipelines implemented?
Yeah, it's a really good question. I'd say in general, solving of the orchestration problem, which is, I would contend, the most critical problem today for data engineering, I think is very much in its infancy today. And it's very much to be expected, right? The last 10 years has been about how do I store more data, process more data, or move it around faster. And we've been basically using bubble gum and baling wire to glue together these pipelines. And it, to me, the industry looks very similar to what container orchestration looked like probably 4 or 5 years ago, sort of the pre-Kubernetes era, right? Where we hadn't moved too heavily declarative-based models with well standardized understanding of what are the components and the building blocks. And we see this a lot, like across different domains. And so what we see right now when companies don't have really advanced orchestration tools, they're using generic workflow engines like Jenkins to just run, it's sort of think of it as like cron with maybe a small DAG, a directed acyclic graph, where they're running a few scripts. There's other open source tools like Airflow or Uzi or Luigi. These are all tools that help you create these DAGs to execute, but they're still it's still just very early because they're running code, but they don't have context. And so, if we look at all the benefits we've seen with the introduction of Kubernetes for running our infrastructure, and how much can be offloaded by the core capabilities of K8s, we've yet to see this really happen in data pipeline orchestration.
If you took a step back, even from organizations that are using Jenkins, you'd find a combination of a lot of cron jobs and manual steps.
Yeah.
Is that fair?
Yep, it's a cron job with a bit of Bash or probably a lot of Bash and Python that's then launching clusters and starting jobs and shipping off either SQL queries to a warehouse or more often than not Spark jobs to a Spark cluster.
Does an organization have some kind of either time constraints or other SLOs in relation to these pipelines?
Pretty much every data pipeline has some SLO, which is always a really brittle thing to accomplish because the notion behind the SLO, usually when you have what is a very manual orchestration approach, right? You have a cron job or some basic orchestration thing that says run this job with this many resources, this many nodes and this much CPU memory, et cetera, at this time. Your data is never static, right? The nature of your data changes significantly. The volumes increase, they decrease, and so all of a sudden, whatever those configuration settings you had that you checked into your repo and your cron job's running at, your SLO is always at risk because the parameters of the data itself will change and the configurations you sent did it. And so that's one of the most brittle aspects of traditional data pipelines is the SLO itself.
You mentioned DAGs, direct acyclic graphs. I want to come back to that when we talk about modeling, but staying on the reliability issue for a bit longer, what are some of the things that can go wrong in a pipeline?
A lot. So pipelines tend to be far more brittle in nature for a handful of reasons. Part of it is we have no data pipeline engine. We have a processing engine like Spark, but we oftentimes don't have the pipeline engine above it that provides that resilience. And so you end up with a few things. Part of it is at an infrastructure level. You lose nodes, you lose jobs. We run, for example, all of our data processing on spot and preemptible instances to keep costs really low for both ourselves and our customers. But those nodes can come in, they can go out. no nodes are fully isolated. You're running other Spark jobs on those nodes at the same time, so you can end up with resource conflicts. And so between node failures, pod failures, potential booming because too much coalesced on a single node or single pod, you tend to see a lot of infrastructure failures that are very recoverable, but you need the intelligence layer on top to know that they're recoverable. The other thing you'll oftentimes see is there's bad data. Like all of a sudden, a corrupted record comes through, right? And having a system that knows what are the semantics of that. Is it okay to ignore that corrupted record, or do you actually have to halt the pipeline and alert on it? Is the second category, more of a data integrity itself. And those are two of the most common breaks we see.
If you have jobs people are depending on them to run, or other jobs are depending, perhaps you have a pipeline that gets data into your analytics database, and maybe you have analytics jobs and people need that data. Do you have a risk of cascading failures?
Oh my gosh, yes, yeah, totally. The cascading failure off of like a broken pipeline that has 18 stages and it gets foobarred at stage 3, and all of a sudden everything else behind it's now blocked. This is like the classic data engineering all the way out to data analyst and the executive report that gets emailed out every morning at 7 a.m. that didn't go out. That's always the scary stuff, and it's the prototypical example of breaks that can be caught early and recovered from, and so on. That creates a lot of friction inside of most companies.
How do people recover when they have this cascading failure? Does someone have to go and restart a bunch of jobs or run them by hand?
Usually, yes. For most, I'd say most folks really end up having to go kickstart the pipeline. It usually ends up being somebody gets paged at 6 a.m. because they noticed that it didn't work. You kickstart the job again, you give it twice as many resources and more memory because it oomed before or something along those lines. You just jumpstart the pipeline again and try and let it catch up. This is one of those ones where we worked really hard. This is sort of one of the core beliefs behind why I even started Ascend was there is a system. There's technically possible to create a system that can be smart enough to say, oh, I know all of the downstream systems, everything and how long it takes and how long it's all historically taken. And I can profile the data and see the profile of the data that's coming in has actually fundamentally changed. I'd say while the standard affair of like, hey, whatever parameters I had before just no longer worked and the thing borked, and I have to kickstart it, that definitely shouldn't be the future. Things like fully dynamic parameterization based off of profiling of the data itself, automated recovery with some level of healthy growth in parameters, like all of these things are very technically solvable problems.
You're talking about, if I understand his last point, job might have failed because either the business has grown, or on that particular day there was more data and it was sized at a certain size and just ran out of resources. So it's not as simple as start the job, run it again, but someone has to look and say, okay, we need to increase the size of this cluster and then try to run it again, and hopefully it'll finish. Is
Yep.
that more or less? Yeah,
Yeah,
okay,
exactly. It
great.
could be, hey, it was Black Friday and we actually just had more people come to our online store than we thought. Like I watch a bunch of the data pipelines we have through our internal systems. And for example, we just do dynamic parameterization of resources. And so you actually can see that it's completely flexes based off of the profile of the data, the complexity of the SQL or PySpark or Scala transforms you're doing. And so it's very possible to flex these resources if your orchestration system understands what's happening to the data itself. And I think that's this next era of orchestration is really around how do we actually have code and data aware orchestration.
Sean, we've been talking about what these pipelines are, what can go wrong in the semi manual world. Are going to talk now more about automation, but preceding that, let's talk a bit about how you model the pipelines, because in order to automate, you do need a bit more rigorous modeling. And that's where these directed acyclic graphs, DAGs, come in that you referred to earlier. Could you expand more on what the DAG is and why is that a useful way to model a data pipeline?
Yeah, great question. So DAGs, the DAGs, these directed acyclic graphs are a way of describing dependencies and an order of operations. Traditional DAGs have really focused on code that essentially say this code, this job needs to run before and successfully complete before this other job runs. And oftentimes it's not just entirely serial, but they can fan out and say this job needs to run, then these three can run in parallel before two of them can run and converge back on one job. But it's a way of describing dependencies of blocks of code. And that's why they become helpful in creating data pipelines is oftentimes you're creating one data set that then flows into another data set that then flows into another data set. And you need these DAGs to specify the dependency of those. They can also, and this is something that we've done at Ascend, which is to restructure it from code centric to data centric, where if you can change that model, for example, if you think about this in a SQL context, you can actually create SQL queries that generate incremental data sets. And then the center of gravity is actually on that data itself and say, this data is a query on top of this data, which is a query on top of these sets of data. And same thing applies around DAGs, just a data-centric approach as opposed to a code-centric approach.
I'm not sure I understood that last point. In some of the reading I was doing about this, if I understood, there's controversy about is the DAG of all the steps you do, like step one, pull the data out of this one database, step two, change all the date formats, step three, load it into the destination database. So we'd have a very simple DAG with three nodes and two edges of steps, or is the DAG about what happens to each element of data? And now, is my question addressing this last point that you made that I didn't fully understand?
Your question highlights what's sort of a traditional DAG, describing the code that says perform each one of these incremental steps. It's more of an imperative construct where just simply describing the take data from one state to the next state. And that's really a classic DAG of, it's a code-centric DAG of perform these steps. The sort of new wave is really around declarative data pipelines. And to be declarative, you actually focus less on the steps of like extract from here, do this, transform, check states, and so on. And instead, you focus just on, I have data over here. I want to transform it with this SQL query that declares the next derived data set. And how data is extracted out, transformed, moved where, and which pieces of data, like what time you run it at, what data has already been processed versus what hasn't, all of that goes away and is the responsibility of the orchestration system in a declarative model with DAGs.
We did another show on Terraform, really focusing on the declarative model, which is useful for the programmer because it may be easier to specify. And then there is some kind of compilation that generates the steps that the underlying system has to take, but it may be easier for the programmer, or maybe you have such a thing as a data pipeline analyst, not to think about it that way. Is that what's going on here as well?
Yeah, very much so. I think we're seeing this move both in Terraform for infrastructure management, for Kubernetes and container orchestration, and now in data pipelines. The declarative approach of just describe the expected end state of your world and have a domain specific, context aware engine that sits underneath it that can figure out how to take you to that expected end state. But I'm obviously very biased towards Terraform and K8s as we use them both extensively inside of Ascend. And so we've been adhering to these models for a really long time.
If the world goes in this direction, or maybe it already has, then is there a job description of the data pipeline analyst who is focusing on coding up these declarative pipelines?
Yeah, I do think so. We've talked about, I actually wrote an article about this earlier on in the year about the notion of the citizen data engineer. We've talked about the citizen data scientists for a long time, people who come in from adjacent domains. And we see a lot of increased demand for data engineers. And historically, data engineering came up through distributed systems, and you had both a math and a stats and a distributed systems background. But the focus was more around moving data around and managing of the underlying systems. And what we see is this notion rapidly expanding around data engineering, which is actually now the fastest growing job for software engineering and tech job, which is the idea being you no longer have to worry about like how many nodes are you running, like have you tweaked and tuned the JVM, and actually don't even have to worry about things like partition persistence and data invalidation and lineage tracking and data integrity. Instead, it is like this data pipeline analyst, as you described, that can up level to focus on the data itself as opposed to the internal and underlying operations. Just as we've seen software engineers be more and more empowered building on top of Kubernetes, we get the same thing for entirely new people able to now build on top of this notion of declarative pipelines, data pipelines, that is.
Now we've covered for a bit how you represent the pipeline. I want to move more into automation. This question, you've probably already answered it, or listeners could figure out what your response would be from things you've already said. You go into an organization and they have a bunch of cron scripts that run and bash scripts. What is a case for automation?
Sleep is usually a good one. Obviously, the listeners can't see my shirt, but I'm actually wearing something that we took at AWS reInvent, which is the pipelines served neat. And it was about it. This pipeline sucks, speak easy, where the joke was there seems to be this very strong correlation between people who wanted the free whiskey and people who had to deal with data pipelines all day. And the the sort of general notion is look like maintaining data pipelines is really hard. They break all the time. We're always tweaking. We're always tuning. And the biggest case for really advanced automation is no different than we saw with Terraform and Kubernetes. Is it makes life easier. You spend far less of your time like plumbing up things and far more of your time actually architecting and designing and building. So for engineers, software engineers who are creating data pipelines, for data engineers who are doing the same, it frees you to spend less time maintaining and more time building.
Is there a name for the broad class of tools which solves this problem?
Not yet. To be really frank, there's I'd say a lot of debate currently what tools fit inside of the broader data engineering suite itself in that ecosystem. We have things for data processing, we have data orchestration, but this is a very generic notion today. Then we also still have a lot tied to the new ideas around data ops, which is borrowing obviously for DevOps, but same sort of core principles of how do we enable more people to build faster safely, just applied to data as opposed to software. And so there's a handful of different categories that, or I would argue subcategories that fit here. But I think ultimately it really boils down to this is at the core, it's data engineering. It's a different kind of engineering that very much needs full-fledged product and full-fledged technology to really help people build faster.
So this question, I'm going to ask you, what is the high-level architecture of a pipeline automation engine? You could either talk about your product or if all the offerings in this space have roughly the same components, what does the generic product look like?
Yeah, that's a great question. The generic product really at the core is a scheduler. I'd say the most common thing we see pretty much uniformly is it's a scheduler that runs some form of jobs with some notion of a DAG. It will usually maintain some level of state. And this is, I think, really where the biggest difference in different technologies comes out is it really comes down to how much state do you maintain? And if you look at it as a bit of a spectrum, cron at one end of the extreme maintains practically no state. A handful of tools will maintain a bit of state. things like they know they ran some job at some period of time. They don't know what the job did or what it produced, but they know that they ran a job and that it maybe triggered another job. So it's a very job centric. We're starting to see things get a little bit better more generically across the industry around some level of maintaining that there's a notion of data. For example, that, hey, I have a catalog I can register data with. But I really believe that the most extreme and really where we've invested at Ascend is how do you maintain the entire notion of jobs and data and the direct correlation between the two? For example, knowing exactly what code produced what piece of data and where, as that's the only way to actually massively automate everything is to have a really tight binding between those two.
I could see if you had a pipeline and it's got 5 steps and there's a failure, systems restart, it would be useful to know, be able to look at some state and say we've done 3 of the 5 steps, at least we don't have to do those 3 again. But if the 4th step involved processing 1 million records and it failed 99% of the way through, if you have more fine-grained state, you could then see we only need to do 1% more and then we'll be done with step 4. Is it my understanding of how the state and the jobs work? Is that where you're going?
Yeah, exactly. It's the knowing where you can pick up from. It's also knowing whether or not you can trust the data. So, like a classic set of data pipelines, some engineer writes code that says, read this data off of this storage system, process it in this way, and then write it back to that storage system. But the question begs is, well, what happens if I change that code? And I'm the next hop, I'm hop number 2 that's processing data. Like, which data is accurate? If I fixed a bug in step 1, how do I know if I have to backfill that data or not? And how do I know if it's been backfilled or not with that bug fix? And no orchestration tool today actually can solve that problem for you, which is it safe to continue to trust that data? And is it now the bug-free set of data? This is one of the things that is different about data pipelines than, let's say, software engineering, where I have all my microservices that are reading on APIs, is when I deploy new code and I make that same API call, but with the fixed code, I'll get the fixed result. In data pipelines, because you persist data along the way, you have to then, if you fix a bug, you have to actually go back and repair data. And that's one of the biggest challenges. And one of the things we worked really hard on at Ascent to solve is binding code to data so that we know if you're changing code, that data may no longer be valid, and that awareness that then the system needs to go repair that data for you. And that's something that is really hard to solve without a really context aware, a data aware scheduler.
If you could solve that, then it would avoid having to delete all the data and start the entire job over again when you fix a bug somewhere in the middle.
You got it. And this is the classic thing that we as data engineers usually do is oh shoot, I found a bug. It maybe affects some of my data, but I don't know which one. Heck, just light up a massive cluster, like do it on a Friday afternoon when all of our traffic's low anyways, and just blast out everything and hope we're done by Monday morning.
I am guessing that many of these individual components of a pipeline are jobs that run on all kinds of different systems, which have their own interface or query language. How does the generic automation engine interface between itself and specific jobs that run any possible place?
Yeah, ultimately, it has to be smart enough to understand the code. You come at it from a couple of different directions. Things you can actually parse, compile, understand, you get a really good semantic understanding of. So if I'm writing transforms in SQL, super easy by comparison to really cleanly understand what's happening with that data, to understand if that data is partitioned, and if something changes, what the impact is. So for languages like that, really easy. Then as engineers start to actually do more complex things in these various steps and transforms of data, really what you do is you look to the developer to tell you hints. Like, so if I'm creating a transform, you're looking for a context of, Is this a reduction, a partial reduction, a full reduction, a map style operation? And when you start to do that, and you provide convenience layers, and for example, a transform in Ascend, you don't have to actually ever worry about the E and the L part. Every transform Ascend's tracking the lineage and maintaining that for you and passing that as a data frame in Spark, a block of data in and out of a function that you write. We alleviate that, but now because we're passing data in and out, we can track all the lineage of that data for you. And so that's the sort of piece of trim down the scope to the common elements and then give the developer all of the flexibility inside of that transform function to do whatever they want. But because we can track the data coming in and out, we can automate the most painful parts, which is the lineage and the profiling and so on.
Well, maybe I'll ask this in a different way because what you said was interesting, but it wasn't what I was trying to understand, which is suppose we have this legacy system and the interface to it is a script, and we need to invoke that as a step. Then how does that integrate with another tool? Is there the orchestration engine? Is there wrappers or
Oh,
sidecars or something around it? Say, you don't know, you're not doing this transform for me. I'm not going to re-implement it inside of some other system. We're just going to reuse pieces we already own. Can you integrate with those pieces?
yeah, some. Obviously, not all, as you migrate various systems. But there's definitely ways as you move from these sort of imperative-based models and more traditional orchestration into more declarative systems to still port over and wrap a lot of your existing systems, or even plug them in together. So oftentimes you can still have a traditional orchestration system dropping off it at a demarc location and continuing to drop there and have the more modern data pipeline pick it up from a particular point too. So we see a lot of people doing it piecemeal.
So Ascend has its own state. You've talked about, is that state stored in some kind of a data store?
It is, yeah. We maintain a bunch of Cloud SQL RDS and then Azure database, depending on which cloud customers in. We store all of that metadata state inside of a SQL database.
So then you're relying on the cloud vendor that they're going to do a certain amount of work to make it redundant and available.
Yep. Yeah, we lean really heavily on each of the cloud vendors to keep we actually run a pretty consistent infrastructure across each cloud, which generally corresponds to a lot of blob or object stored usage. Kate's and all three clouds run dual clusters, one for control plane, one for processing, and then heavy of their cloud SQL databases.
There's concept in the messaging space, at least once delivery, meaning I send a message, I want the system to always fail on the side of it's going to get there eventually, and if it gets there twice, we can live with that.
Mm-hmm.
This sounds like the type of guarantee you want. You want every piece of data to be processed, and if you process something twice and get the same answer twice and write it in the endpoint twice, that seems like no one would even notice. Is that the right kind of guarantees for a system like this?
Yeah, it is. Especially for like big data pipelines that are moving around big blocks of data, you're looking for those sorts of guarantees and a couple of others, and you're looking for those for blocks of data as it moves through. And so you're looking for a few things. Like one is you're looking for commits of data. So oftentimes you have data that's sitting under a particular data product, right? It's a unified data set, and you're updating one partition of data. You need to make sure that you can commit that partition of data that may actually be 5 different files, part files inside of there. And you need the ability to atomically commit that and integrity check it, and then garbage collect the old version of that partition before you trigger the downstreams, right? So you want that ability to one deliver it, potentially update it, which you don't necessarily have in message delivery in the same way, and then know if it's a partition of data that had a previous version associated with it, where did that entire partition go, and how do I follow the previous calculations and update those accordingly? And you need to do all that at atomic stages where each one's committed.
So you have stages and you're going to rely on an underlying substrate like a blob storage to commit chunks of data that you've processed, and you have metadata that's going to some kind of database. Is there any issue of you want the overall, all the stuff you do when you've completed a step, which is going to include blob storage and updates to metadata, to be atomic, or can one of those fail and the other one succeed?
Generally, if one of the steps fails, you generally want to retry. And we put in a bunch of safeguards. For example, everything we write into the object store is immutable by design. We actually generate random IDs, and every incremental run, every attempt is always written to a different path. So you never have to worry about multiple attempts or jobs all colliding with each other. And then we use at the metadata layer, we actually use content addressable storage to not only point to the right block, but actually even do things like deduplication. If I'm running multiple pipelines that are actually trying to run the same code and generate the same piece of data, you can do things that deduplicate all of that. This is why we run the micro batch approach. Is you run a step, if it fails, you can retry it, write it to a different stage, commit that at the metadata layer, and then trigger the downstream system and make sure that things continue to ripple.
One of the areas I could see where automation would really help is if there are steps that you could do in parallel, you can get the end result faster, but that does create very difficult programming challenges, which are similar to what you have in multi-threaded programming, where you're trying to get multiple threads to all synchronize at an endpoint. Is that something that Ascend or orchestration engines can help you with?
Yes, they absolutely do. The DAG helps here. It's funny, we actually have both our head of product and our CTO are former chip designers with PhDs in electrical engineering. So there's a lot of chip design influence in how we built our system. And the general idea is, yes, anything you can parallelize, you should. When the system's data aware and can bind data to code, you know when those actually converge at the DAG. And so you can run these in parallel, which is super cool. And then you can even do really other neat optimizations, like specifying priority and inferred priority from up and down streams to make sure that the higher priority stuff gets all the resources it needs if you maxed out on the number of resources in the cluster. So you start to do really cool optimizations based off of just tiny bits of metadata that the user may provide.
You could be talking about a case where we have 6 things that are parallelizable. And if we had enough resources, we could do all 6 in parallel, but we don't have enough resources to do 3. So the tool will figure out orchestration. We can do these 3 first, and then those 3. And as a programmer, you don't have to think about that.
Exactly. You just say, as a programmer, you say, I have these 6 things that need to happen. They need to converge, and this thing needs to happen after they converge. And here's what's more important than others. And the orchestration system's actually smart enough to do things like say, hey, I know I had auto scaled down to just 5 nodes, but now I need 30 nodes, so let me spin those up. And as soon as those nodes are available, start shoving as much work as I can towards them. And it can take care of all of that for you automatically. And it just tracks dependencies. And once dependencies of everything is met, it just moves forward.
That type of programming, it's quite difficult to do if you try to code it up yourself.
That's like the first 10 years of my career. Yes, it's very
Okay.
difficult.
All right. So let's wrap up the discussion of the architecture and orchestration. Talk about monitoring first. Let's talk about what would you want to monitor about your pipelines.
Yeah, so when you're monitoring your pipelines, the things that you're really caring about here is one, if you've implemented data integrity checks, you really care about if one of those integrity checks has failed. For example, some of our customers have implemented pipelines that say, if this integrity check fails, I want you to halt everything and just page me because something really bad happened. Like somebody tried to put in wrong data. And so that's one, which is purely data integrity. The second thing that you really want to monitor for, honestly, with data pipelines, and this is usually more of an InfoSec thing, is you want to actually monitor who's working on those data pipelines. And so there's a lot of, this may not be an alerting, but this is definitely a monitoring, is you want to know all the changes that are being made, who's making them, who's accessing data, and that's a really important part of security. So you need to make sure you're doing that. And we have a bunch of customers that essentially have integrated into like Sumo Logic or Splunk all of the access data that comes out of Ascend to make sure that they have all of that. Then the third thing that you're looking for as you kind of go down stack is you really want to monitor all of the performance. You want to know how fast are your pipelines running. You want to know how many resources they take. And then you're actually, for most people, if you're not using like a declarative orchestration system like Ascend, you end up doing a lot of how many nodes am I running? How packed are they? What's the utilization of each one of those nodes? Where are the performance bottlenecks? Am I scaling up fast enough? Am I scaling down efficiently? And a lot more of an infrastructure tuning. And some of that you get when you're running on like EMR or Qubole or Databricks, but a lot more of it comes into the what are you sending to the jobs there. And so that's an infrastructure efficiency. And then the fourth is actually in our world of Spark efficiency, which is how much data are you reprocessing unnecessarily? So oftentimes it's are you sending the smallest, most compact, most efficient jobs to your processing engine at all, or are you doing a lot of inefficient reprocessing of data? And that you can measure very quantifiably. So those are really the four things that are valuable to monitor. Four categories, I should say.
We did a episode on distributed tracing. I could see that either might or might not be useful in this pipeline context. What's your take on that?
Yeah, so it's a really good question. Especially across microservices, distributed tracing, super, super valuable. Inside of data pipelines, it's a relevant concept, especially as it pertains to the data itself, knowing where did this piece of data go to? And I think that's one of the ones that for most folks is really hard to know. In a classic orchestration, if you're not tracking, you don't have a system that has an understanding of the data and the code itself, it's really hard to know where is everywhere that this individual piece of data went. And that really kind of goes back to, again, having a data aware system that knows this piece of data, this was run on by this piece of code, and it went to all of these 18 different hops and transform.
Is there a need for some kind of audit trailing?
Yes, definitely is. We actually we were getting at Ascend, we were getting a lot of requests for this for about a year. And just about a month ago, we even released a product called Ascend Govern. Basically, because we have such this data aware system that's super smart about knowing where everything came from, we really quickly realized that, oh, actually, we could just pop an API up on top of all of our internal metadata that's doing all of these calculations. And all of a sudden, you could actually say, hey, for this transform on data and this column, tell me all of the code that generated the inputs of this and everything that fed into here. And vice versa, this one piece of data, where's everywhere it went to? So part of that govern release was our entire lineage API that gives you really good and really cool insights into basically just what's happening to all your data, which is fantastic from an auditability perspective.
I could imagine that privacy regulations might impact this area as well. As how would that work?
Are you talking about like GDPR, CCPA?
Yeah, things like that.
Yep, totally. This is one of those ones where, when we talked about before, hey, if you change your code or you fixed a bug and you have to go and backfill data and rerun everything, same kind of thing happens when you have to scrub data for GDPR. If a consumer exercises the right to be forgotten, you have a lot of their raw data sitting somewhere in a lake. You have to go find everywhere that piece of data has gone, and you have to go get rid of it. And this is in a classic data pipeline world is really hard if you don't have all the lineage and the auditing and so on to know what has to actually get those. It's not just inserts or additions that get propagated, but deletes have to actually get propagated too.
And one final question. You mentioned some of the tools in this space, like Airflow and Beam, and I can see for some sets of problems you could accomplish this with Hadoop or with some of the abstraction layers on top of Hadoop that are more declarative like pig or hive, where if you have your own infrastructure, then you can just run these tools on your own infrastructure versus more like a hosted solution, a pipeline automation as a service. Where do you see things going in? Do you think this will be just another feature that all the cloud vendors, if they don't already have it, will offer it as one of their product lines?
Obviously, I'm really bullish and optimistic on the need for more advanced scheduling and orchestration. Technologies like Pig and Hive, for example, I've used Hive a bunch in the past. These all, technologies sit on top of that processing engine, and they provide a great query, or Hive does provides a great query interface that compiles down into Hadoop jobs. And basically what you get out of this is kind of like what you get with Spark SQL that runs on Spark, which is a queryable interface that has a query planner and a query optimizer. The missing link is still on top of that is you ran a query at one point that generated some data. When you think about the data orchestration for data pipelines that are continuously running, what you really actually need is like this continuously running query planner and query optimizers that is perpetual, that is constantly running to just tracking everything that's moving all the data through, as opposed to just for one query and snapshot in time. And so I think that is where the next big frontier is, because that's where we're spending all of our time right now. And so I do really believe that when we look at things like infrastructure management, container management, data pipelines is one of these next domains where we can move things towards more declarative models that have these domain-specific service or scheduling and orchestration layers that really can optimize. And so to the latter part of your question, wholeheartedly believe, yes, we're going to see all of the cloud vendors continue to try and invest and expand here, because it's the thing that gives data engineering teams so much leverage and freedom to build more faster.
Sean, where can listeners find your company?
To find our company, we are at ascend.io, ASCEND.io.
Where can listeners find you?
I am on Twitter and LinkedIn, and very rarely on a few other platforms, but I would stick with Twitter and LinkedIn under my name, just at Sean, SEAN, Knapp, KNAPP.
Great. Put that in the show notes as well.
Great.
Sean, thank you so much for speaking to Software Engineering Radio.
Thanks so much for having me, Robert. This was a ton of fun.
This has been Robert Blume. Thank you for listening.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.